All right, so let's take a look at problem 5. Problem 5. In a clinical trial of an allergy medication, 120 people are treated with the medication and 100 were given the placebo. And we can see that here. We have 120 total who got the medication and 100 were given the placebo. A control group consists of 80 people who were given neither the medication or the placebo. Okay? This is the number of people who showed improvement in the table. So we have the people who improved, 138 improved, and 168 who did not improve. And it shows the relation, right? Those who improved and took the allergy drug were 65. Those who did not improve and took the placebo, there were 58 of them, right? So we're going to use this table to calculate the probabilities. Remember, you always have to find the sums of your columns and your rows, right? That's really important. So let's take a look at some probability problems. I know everybody's fave. So, what is the probability that a randomly selected person was given either the drug or the placebo? The or means I want people in both groups. So, those who were given the drug was 120. Those who were given the placebo was 100. And that was all out of 300 people, right? Our total sample size. That gives you 0.73, so 73%. What's the probability that a randomly selected person either improved or did not improve? Well, those who improved was 138. Those who did not improve was 162. That's all out of 300. Now, we only had two options. You either prove or you don't improve. So that gives us a probability of 1. Okay? What's the probability that a randomly selected person had no improvement? Well, those who did not improve are in this row right here, and that's going to be 162. So 162 out of 300 did not improve, and like I said before, you can leave this as a fraction or write it as a decimal or as a percentage. I don't care. Part D, what's the probability that a randomly selected person was given the drug and improved? This and looks for the intersection. So I want to see who was given the drug and who improved. That's going to be 65 right here. So 65 out of 300, that's whether they were given the drug or they improved. So that gives me 0.216, which is 21.6%. Now, this last problem, this is the only one that ever trips people up, okay? So, I want to know the probability that a randomly selected person was given the drug. So, that's this column right here. I should use something other than blue, shouldn't I? Given the drug or improved. So, I want all the people in here. Now, the way we do this is by taking all those who improved plus all those who took the drug, plus all those who improved. But the problem is I counted these people twice, right? I counted them because they took the drug, and I counted them because they improved. So I have to subtract that. That gives me 0.643 or 64.3%. The reason we didn't have to, in part A, remove something that was double counted was because these two columns didn't have any overlap. It was the probability they were given the drug or given the placebo. And there's no overlap in those columns, as you can see. Next, pulse rates for adult females are normally distributed with a mean of 74 beats per minute and a standard deviation of 12.5 beats per minute. This data set sounds familiar. What I want us to do is use the 68, 95, 99.7 rule to find the following values. Now remember, the 68, 95, 99.7 rule tells us what percent of data is within either 1 standard deviation, 2 standard deviation, or 3 standard deviations on a normal curve, right? So remember, our mean divides our entire data set in half, right? That means 50% on one side, 50 on the other. Within the first standard deviation, I have 68% of the data. Within the second standard deviation, I have 95% of the data. And then within 3 standard deviations, I have 99.7% of the data. And like I said, within the first standard deviation, I've got 68%. So that's how this rule works. So we're going to use this rule, not a z-table, to get full credit, right? In order to solve the following. So I want to know what's the percentage of pulse rates less than 74 beats per minute. So let's go ahead and fill out our table. So I have my normal distribution. My mean is 74. And I want to know what percent of pulse rates are less than 74. Well, because 74 is my mean, it divides my data set in half. So I've got an area of 0.5 on either side. So it's going to be 50%. That was a nice, easy one to get started. So 50% of pulse rates are less than 74. I want to know what percentage of pulse rates are between 49 and 99 beats per minute. So why don't I go ahead and in blue draw our normal curve that we're looking at over here. I've got 74. If I go up 1 standard deviation, that puts me at 86.5. 2 puts me at 99. 3 puts me at 111.5. So 3, 2, 1. And remember, these are negative standard deviations. Now I need to go look at the negative standard deviations. That puts me at 61.5, 49, and 36.5. Okay. So I want to know what percentage of pulse rates are between 49 and 99 beats per minute. Well, 49 and 99 both mark our second standard deviations, so it's going to be 95%. Next, I need to know what percent of pulse rates are between 36.5 and 111.5. Well, that marks our third standard deviation, okay? So that's going to be 99.7%. Now, what if I want to know what percentage of pulse rates are greater than 99 beats per minute? Well, 99 marks the second deviation, and I know I've got 95% of data in here, okay? That means I have 0.05 in either of my tails. Well, 0.05 is divided by 2 is 0.025, so that would be 2.5%, because I want to know the area on this one. 2.5%. Next, I want to know what percentage of pulse rates are less than 86.5. So I'm going to clean up my mess a little bit. Give us a little more room to work. Okay. Let's redraw our beautiful normal curve here, right? All right. I want to know what percentage of pulse rates are less than 86.5. Now, 86.5 marks the first standard deviation, and my mean divides my standard deviation in half. So what percent of data is within the first standard deviation? Well, that's going to be 68%. So that means I've got 34%, which is 68% divided by 2 on both sides. I also know, so that's right here is 0.34. I also know that my mean divides everything in half, so everything over here is actually 0.50. So I'm going to take 0.50 plus 0.34 and get 0.84. So 84%. So that's how I want to see you guys work through these problems. I want you to sketch it out for me. Okay? Sketch it out. Next, we're doing an ANOVA test. This is an example of an ANOVA. The vertical semi-restrained test was used to conduct flammability of children's sleepwear. Pieces of fabric were burned, and after the burning was stopped, the length of the burnt portion was measured. Okay? And we looked at the same fabric samples being tested in 5 different laboratories. And the analysis of variance is shown before. So I've got my p-value here, I've got my f, okay? I want to know what my null and alternate hypotheses are. So my null hypothesis is that all the means are the same. Mean 1, mean 2, so all the laboratory means are the same. My alternate hypothesis is that one of the means is different. At least one of the means is different. Okay, next it says identify the p-value. This is really nice because we didn't have to do any math. The p-value is right here. It's 0.03. 1. Next, I'm going to use this p. Remember, this is our p-value. This is our probability. I'm going to use this p-value to make conclusions about my population means. So either reject or do not reject my null hypothesis. So let's do this for two significant levels. What are my two significant levels? 0.05 and 0.01. If I were to look at the 0.05 significance level, because 0.03 is less than 0.05, I reject my H naught at the 0.05 significance level. But what about if my significance level is 0.01? Do I reject or not reject my null hypothesis? Well, I don't reject my null hypothesis because 0.031 is greater than 0.01. So I do not reject my null hypothesis at the 0.01 significance level.